Okay, let's get started. Welcome everyone to our 7th Compass lecture of the fall 2022 semester. To this week we have Kishore Patra speaking on tidal disruption events. Kishore Patra is a PhD candidate working with Professor Alex Filipenko in the Department of Astronomy. He is broadly interested in astronomy with current focus on supernova explosions, tidal disruption events, and exoplanet orbits. He has a specialized expertise in the technique of measuring polarization as a function of light wavelength. Before coming to Berkeley, he graduated with a BSc in physics from MIT in 2018. At MIT, he worked on the search for orbital decay in short period exoplanets. He grew up in a little village on the eastern coast of India before moving to the UK and then to the US for higher education. In his free time, Kishore plays cricket and tennis, explores maps, and writes stories. So everyone, please, let's welcome Kishore. Just be sure to unmute yourself on your end.
Should I keep the volume on?
You can mute the volume, and we'll interrupt if we have any questions in the chat.
Sounds good. All right, well, thank you for that lovely introduction. And thank you all for being here in the room and all over the Zoom. So I don't know about you, but when I was growing up, I was pretty scared of the term black holes. And I sort of like blame the media for that because, they often portray black holes as these giant, mysterious, hungry monsters that are ready to gobble up everything and they will destroy everything in their path. And I think part of the reason why perhaps that image has been developed for black holes is that black holes for the longest time were just a theoretical curiosity. And many early pioneers, including Albert Einstein, did not believe in the black hole's physical existence. But fast forward 100 years, and now we have plenty of evidence for the existence of these very strange cosmological objects. So a black hole is a region of space-time with gravity which is so strong that nothing, not even particles, not even light, can escape from them. And the last surface where light can still escape is known as the event horizon. And unfortunately, black holes are not directly observable because they don't emit any light. And for astronomers, light is the most important tool for how we study any astronomical object. So if you don't have any light coming from them, so we have to rely on indirect ways of detecting and studying black holes. So take, for example, this image that you're seeing on the screen. This is the black hole at the center of a galaxy by the name M87. It was imaged just a few years ago by the Event Horizon Telescope. And what you see here is not the black hole itself, but the disk of gas around it, which is hot and it's glowing. And it's been hypothesized that almost all galaxies in the universe have a supermassive black hole at the center of those galaxies. And a supermassive black hole, this means a black hole that is, as the name suggests, it's very massive. Typically, although there's no clear definition of a supermassive black hole, typically a black hole that's more massive than 10 to the 5 solar masses would be considered a supermassive one. So we know that the Milky Way also has a black hole at its center. How do we know that? Well, starting late 90s, astronomers, and including some astronomers at UC Berkeley, began tracking trajectories of stars near the galactic center. And they found that they all seem to orbit this invisible object, which was no larger than 5 times the sun's radius. But the weird thing was that this tiny invisible space contained mass of more than 1 million solar masses. So very high mass condensed down to a very small region. What could it be? So that at that time, this was consistent with the presence of a supermassive black hole at the center. But now, of course, we have directly imaged the galactic center, and what we see is this. So this is the image of the black hole at the center of the Milky Way. The name is Sagittarius A star. The image is not as clear as the M87 for many other reasons. But what we are seeing again is this disk, the disk of gas and dust around the black hole. So the interesting thing here is that we are able to study the black hole in M87 and in the Milky Way because these galaxies are pretty close to us. I mean, we live in Milky Way. So these black holes are close enough that we can study and resolve individual stars around these black holes, or study or directly image the gas disk around these black holes. Well, what about the gazillion other black holes out there in other galaxies? How do we study them? We can't resolve individual stars in them, and we can't, directly image the disks around them either, because our telescopes simply don't have the resolving power to do that. So what do we do then? Well, luckily there is a way to study black holes in other galaxies. Well, technically there are two ways. One of them is the gravitational waves. So if you have two black holes that orbit each other and merge together, then they release a ripple in space-time that can be detected by these specialized detectors known as, for example, LIGO, which stands for Laser Interferometry Gravitational Wave Observatory. But LIGO cannot detect black holes which are standalone, like at the center of the Milky Way. So how do we study those? So for those galaxies, those black holes, we need something else. We need the sacrifice of a brave star. So let me ask you this question. So I'll ask you this question, and I would like you to answer it using your fingers. If you think the answer is A, you can just raise one finger, 2 fingers for B, 3 for C, and D, 4 for D. Yeah.
Sorry, I had to turn on the captioning and it put a window up there. You can look close on that.
Okay. It's all good. All right. So the question is, a star comes sufficiently close to a black hole. What happens next? Option A, the star is sucked into a black hole like a vacuum cleaner sucks dust. Option B, the star remains intact, but falls into the black hole, never to be seen again. Option C, the star gets spaghettified and all of the star's gas falls into the black hole. Or option D, the star gets spaghettified, but only a small fraction of the star's gas eventually falls into the black hole. So take about 10-15 seconds to think about it. And when prompted, just raise your finger. And you can raise them under your chin so that, if you don't want other people to see what you're answering. All right, if you're ready, let's go. Answers? Okay, so there's general consensus, but there is some difference there. And let me just quickly check the chat. Okay, there seems to be similar answers in the chat as well. Okay, great. So let's actually go through these answers and these options and see what's the right answer. So the first option is that a star is sucked into a black hole like a vacuum cleaner sucks dust. So this is actually a general common misconception. And I actually have to again blame the media for this, because they portray black holes as these monsters that are out there to get you. But black holes don't do that. They're not like vacuum cleaners. They're just objects with very high gravity, and those effects of gravity only become relevant when you're really close to the black hole. And by close, I mean a few times, say, the size of the event horizon. But far away from the black hole, space-time is pretty normal. So imagine by magic, if the sun somehow became a black hole just in an instant, gravitationally, you would feel nothing different. The Earth will continue to orbit around the sun as if nothing happened. Of course, there won't be sunlight, and that's another, whole other issue. But, gravitationally, we would feel nothing. So option A, we can definitely rule that out. That's not what happens. Now, I will talk to you about options B, C, and D, but that will come a bit later, okay? So let's actually go back to a black hole and try and understand how is it that black holes cause tidal disruption in the first place. So the most important property for a black hole is its mass. The mass determines the size of the event horizon. And that size of the event horizon, also known as the Schwarzschild radius, goes as 2gm over c squared, where g is the gravitational constant, mbh is the mass of the black hole, and c is the speed of the light. Now, let's say that we put an astronaut or any person near a black hole. And remember that the gravitational force goes as inverse squared of the distance. And that means the head of this person will feel a smaller force compared to the legs of this person. So there is a differential force across the length of this person. And that differential force is known as the tidal force. So that is, generally what we mean by tidal force in astronomy and physics. So imagine a star that comes in on some orbit, and the star will also feel the tidal force. The part of the star that is closer to the black hole feels a stronger pull, stronger force compared to the star that is away from the black hole. And as the star goes on its orbit, it comes to this critical distance where the tidal force becomes so strong that it actually overcomes the self-gravity of the star, and that causes the star to be tidally torn apart. It's now called a tidally disrupted star. And that critical distance is given, it also depends on the black hole mass, but it also depends on the star itself, the size of the star or star, the mass of the star as well. Now, note this interesting thing that the Schwarzschild radius, the size of the event horizon, grows linearly with the mass of the black hole. So you double the mass of the black hole, the Schwarzschild radius doubles. But the tidal radius grows slower. It grows only as 1/3 of the mass of the black hole. So that leads to some very interesting consequences. What happens is that as you increase the black hole mass, the Schwarzschild radius will actually catch up to tidal radius and eventually be larger than the tidal radius. Let's look at that a little in some detail. So here I am considering a sun-like star that interacts with a black hole. If the black hole has 10 to the 6 solar masses, that's 1 million solar masses, then its tidal radius, which is shown in orange, is much larger than the Schwarzschild radius. So any star that comes within the tidal radius will get disrupted. But if you increase the mass of the black hole by a factor of 10, then your Schwarzschild radius and your tidal radius both grow in size, but the Schwarzschild radius grows much more than the tidal radius does. So a star that interacts with this black hole will still get disrupted. But if you consider a black hole of mass 10 to the 8 solar masses, then that star would not get disrupted. It would actually simply just fall into the black hole and disappear. Now consider a fixed black hole mass, and let's consider 3 different kinds of stars. So a red giant star would get tidally disrupted at a much larger distance. That's because a red giant star is very big, and the surface layers of a red giant star are only tenuously bound to the red giant star. So it's easy to disrupt a bigger star. Then a sun-like star would have a tidal radius, which is smaller than the tidal radius of a red giant, and a white dwarf's tidal radius would actually be inside the black hole. So a 1 million solar mass black hole cannot tidally disrupt a white dwarf star. So this is pretty weird. In fact, this seems to show that the bigger the black hole, the more benign it is. It's actually the smaller black holes that can really wreak havoc on your health. And this sort of explains also why, if you have seen the movie Interstellar, there's an astronaut who falls into the black hole. But the first time I watched this, I thought, why isn't this guy getting torn apart? And the reason is that this black hole that he falls into is a supermassive black hole. It's not a small black hole. So the tidal radius is actually inside the black hole, and that's why this person falls right away without getting disrupted. Now, at some point inside the black hole, they might still get disrupted, but that's pure speculation. Okay, so that brings us to the option B. B is a possible option, but it requires certain specific conditions. You need a really large black hole for the star to remain intact and fall into the black hole, just disappear out of our sight. By the way, feel free to interrupt and ask me any questions in between. So let's actually go back to a black hole to a star that does get tidally disrupted. So imagine a star that comes along in an orbit. At the tidal radius, the star will get disrupted. But at that point, the star also has a spread in orbital energies. And what that means is that the part of the star that is closer to the black hole is more tightly bound compared to the part of the star that is away from the black hole. And that spread in energy is given by the gradient of the potential multiplied by the size of the star. And because at the tidal radius, the gradient of the potential is so high, you can actually give the star a really large range of energies. The consequence of that is that roughly half of the star is actually in highly unbound orbits. So half of the star is just flung out into the space and never comes back to the black hole. But the other half, which is unfortunate enough to stay in bound orbits, will stay there and form an accretion disk. So in the classical, let's go back to the option C. So we can rule out option C because not all of the star's gas will fall into the black hole. We know that at least half of it goes away in unbound orbits. Okay, so we've established that roughly half of the star is in bound orbits. So what happens to that bound debris of star? So in the classical picture, which was developed in the 70s and the 80s, it was understood that this bound debris would quickly form an accretion disk around the black hole, and the accretion disk would slowly feed off the mass to the black hole. In the classical picture, there is such high velocity of this gas that's swirling around that there's a lot of friction that's generated, and it actually heats the gas to a very high temperature, typically up to 10 to the 5 Kelvin. And at those temperatures, the gas would emit light primarily in X-rays. So in the classical picture, black holes are very efficient converters of gravitational potential energy into electromagnetic radiation. And the result is this luminous, very luminous flare that can rival the likes of supernova explosions. So initially, TDEs were discovered in the X-rays as expected. But in the last decade or so, people started discovering a new kind of TDE known as the optical TDEs. And what was strange about these was that they were much cooler. Their temperatures were typically 10 to the 4 Kelvin. They peaked in the UV and the optical wavelengths instead of X-rays. And in fact, they showed very little X-rays, if any at all. So we call these TDEs the optical TDEs. And they differ from the so-called classical TDEs. So here I'm showing you what is known as the light curve of a TDE. So it's just, what it does is it's just a measure of brightness as a function of time. And you see that there initially, for all of these curves, which are, each curve represents a different filter or different wavelength bin that observers use. And you see that all of these light curves rise up initially. That typically takes about 50, 60 days for the luminosity to increase, reach a maximum. And then the luminosity goes down over the course of, roughly 100 days or 1 year or so. So this is a very typical behavior for a tidal disruption event. For optical TDEs, what's weird is that they show very little X-ray emission compared to emission in optical wavelengths. So here I'm plotting the ratio of the luminosity in optical, denoted by LBB, and Lx is the luminosity in X-rays as a function of time. And there are 4 different TDEs shown on this plot. And you see that these ratios span a huge range of orders of magnitude. So some of these TDEs have 1,000 times more optical emission than X-ray emission. And none of them actually have dominant X-ray emission. So this leads to a very interesting question. The question is, why do these TDEs, these optical TDEs, not have X-ray emission? I mean, the classical picture, which is so well understood, is that there should be a lot of X-ray emission because the disk should get that hot. So why is it that these TDEs not show any X-ray emission? And this is one of the biggest open questions in the field of TDEs right now. And 2 solutions have been proposed to answer why there's not enough optical emission. And they basically have to do with how quickly the accretion disk can form. So let's look at the first solution. So the first solution says that the accretion disk forms very quickly. And by quickly, I mean in a few tens of days. So here's the accretion disk in the middle. The black hole is the black dot at the right center, at the very center. So the disk does get very hot. It does produce a lot of X-ray and high energy emission like extreme UV emission. But in this picture, what happens is that as the gas gets hotter and the radiation becomes more intense, the radiation pressure can actually blow some of the gas out in a wind. So if you have this wind that is emanating from this accretion disk, it forms a cloud around the black hole and the accretion disk, obscuring our view of the accretion disk. And that means any high energy photons that are generated in the disk have to fight and struggle through this gas cloud as they come out. And in the process, they get absorbed, re-emitted, scattered by free electrons. And each of these processes take some energy out of that photon. So by the time that photon finally escapes out of this cloud, it has gone all the way from X-ray emission down to optical wavelength. So this sort of like neatly explains why in these optical TDEs, you don't see much X-rays and you only see optical emission. Now, in this picture that I'm showing, I'm just showing you a cross section, but you have to imagine that the yellow part, the yellow gas cloud is all enveloping. It is completely obscuring the view of the accretion disk. Right. So one may ask, like, why is there a mass outflow in the first place? And that has to do with the fact that once you heat the gas to such a high temperature, some of the gas particles may attain escape velocity, so they will just simply escape. But also, the radiation becomes so intense that the radiation pressure will also drive a wind. In literature, this is often called an Eddington wind. So that's one solution. The other competing solution for why there is optical emission and not enough X-ray emission is the following. So in this picture, in this model, the accretion disk does not form immediately. It takes a long time to form, typically several hundred days to form an accretion disk. And what happens is that as the star gets disrupted, the tidal stream actually collides with itself. So you can imagine there's a funnel of gas coming in. It goes around the black hole and collides with its own stream. And that collision is such high velocity and so impactful that it locally heats the gas to a point where it would actually produce a lot of emission. And most of that emission would be in the optical wavelength range. So those are the two models. So in this model, there's no need for an outflow. It's just all shocked gas that is hot enough to be emitting in the optical wavelengths. So to distinguish between these two models, we need to know what happens to a star's gas right after disruption. Does it form an accretion disk promptly and have a wind outflow? Or does it result in a slow accretion disk formation and instead the optical emission comes from the shocked gas? And because we can't resolve, we can't take an image of these distant black holes. So we can't directly study these. And so we have to rely on an indirect method. And one novel way to study the geometry of gas is by studying polarized light coming from these tidal disruption events. So what do I mean by that? So any electromagnetic radiation has electric field and magnetic field. And the polarization of that wave is given by the direction in which the electric field is oscillating. So in this wave, the electric field is oscillating in the y direction. So this wave is polarized in the y direction. Now, light from most astrophysical sources is unpolarized because, for example, sunlight coming to you has electric field vectors, oriented in all random directions. So the net result is that you don't see any net polarization. But in TDEs, you have a lot of free electrons. So the gas is hot enough that it gets ionized. So there is a sea of free electrons that can scatter the waves. And the idea is that if you have an incoming electric field that will oscillate the electron in the same direction as the electric field, and that should result in some polarization at an observer's position, which is the projection of that oscillation in the observer's direction. And in the field of studying polarization, we denote different directions by, we give them different letter names. So if your polarization is up and down, we call that Q. If it's 90 degrees horizontal, that we call them minus Q, and the other directions are called U and minus U. Those are just conventions, but in literature, you'll find them called as Stokes parameters. They are the decomposition. The Stokes parameters are the decomposition of the polarization vector. So here's the idea of how to measure, how to deduce geometry from studying polarization. So imagine you have a very spherical source of light. It's perfectly spherically symmetric. So in that case, what happens is that all these electric vectors, they all add up to 0. So the white arrows show the electric field, the position, the magnitude, and the direction of the electric field in that local region. And if you add all these, integrate these electric fields across the surface, you get 0. But let's say you had some asymmetric source. In that case, when you integrate over the electric fields, you get some non-zero residual. In this case, that would translate to roughly 1% polarization. So the idea is that if you measure polarization from a source, it tells you that the source is not symmetric, not spherically symmetric. Whereas if you measure 0% polarization, then you can tell that the source is pretty spherically symmetric. Now imagine if you were to squish the source all the way down to a thin line. So like the most asymmetry that you can possibly have. In that case, the maximum polarization you would measure is about 11%. So you need fairly sensitive instruments to measure these kind of low levels of polarization. So related to this, now let's relate that back to the two models. In the reprocessing model, the gas, the wind coming from the disk would form sort of like a spherical cloud. And in that case, the hope is that if we measure polarization, we should see the polarization to be very close to 0. But in the shocks model, because it's inherently an asymmetric process, we expect that the polarization should be a few percent, like 4 or 5%, but less than, somewhere between 0 and 11%, but typically more like 4 or 5%. So that's the game. So we go out, we measure the polarization, and we figure out whether the polarization is low or whether it's a few percent, and that could help us distinguish between these two models that attempt to explain the source of the optical emission. So that's what we did. So a couple of years ago, there was a TDE. We gave the name of that TDE is AT 2019 QIZ, 2019, because it was discovered in the year 2019. and AT stands for astronomical transient. So it was one of the nearest TDEs to date, only at 65 megaparsecs. For reference, the Andromeda galaxy is roughly half a megaparsec away. So it's still, pretty far away, but, as far as the, the cosmological scales go, this is, just in our backyard. And this TDE is a normal optical TDE. And what I mean by normal is that it does not have a relativistic jet coming out of the middle. Now, jet can complicate things a lot. Jets have their own non-thermal processes, which can actually contribute to polarization. So if you have a jet, then typically you can't really study the geometry very well. So it's a good thing that there was no relativistic jet, because then in that case, we can study the geometry pretty directly. The temperature of this disk was measured to be roughly 2 times 10 to the 4, 20,000 Kelvin. The black body luminosity, the black body equivalent luminosity of this TDE was on the order of 10 to the 43 ergs per second. And if you convert that to, if you integrate that over a year's time, roughly a TDE would last roughly a year. If you integrate that to find the total energy emitted by this TDE, that comes out to be roughly 10 to the 51 ergs. And that's on par, comparable to the brightnesses of luminosities of supernovae explosions. So this is a very, very bright event. And the X-ray luminosity, which is denoted by Lx, was actually, at least 2 orders of magnitude lower than the optical emission. So yeah, so all things indicate that this was a very normal optical TDE for which we could study the geometry pretty well. Here's the light curve of this object. So what I mean by that is that the brightness increases over time, reaches a maximum, and then goes down. And by these red lines, I'm showing the 2 times when I got the polarization measurement. So the first measurement of polarization we got right at the maximum brightness, and then we got another measurement of polarization a month later. And the good thing about having 2 separate measurements is that we can see how the geometry of the gas changes, how it evolves over time. I mean, in an ideal world, I would have liked even more measurements, but these are very hard measurements to make. And there's not enough telescope time to go around as well. Okay, so what does the polarization measurement tell us? So here's the polarization measurement. In the top panel, I'm showing the regular flux spectrum, which is just a brightness as a function of wavelength. These green lines, these green vertical lines, are the hydrogen Balmer lines, H alpha and H beta. There's also a helium line there. That's the supposed location of the helium line. And these cyan vertical bands are the locations of where you typically get absorption from the Earth's atmosphere. So in these regions, you typically get a lot more noise. So it's just good to mark them just so that you don't get fooled by any spurious signal. The middle panel shows polarization percentage. So what percentage of light was polarized? And we see that the polarization is consistent with 0%, across the entire wavelength range. And then the third panel shows the polarization position angle. You can think of the polarization position angle as the orientation of the net polarization on the sky. So 0 degree would mean that the net polarization vector is pointing north in the north-south direction. And 90 degree would mean that it's pointing in the east and west direction. So these results are actually very consistent with this reprocessing picture. So we think that this in this particular TDE, there is a strong outflow, wind outflow, and that creates this spherical cloud that obscures the disk that resides in the middle. And this outflow has a very spherical shape. That's what the polarization data are telling us. To give you a sense of the scale, so the black hole is right at the middle. It's only about 5 times the sun's radius. The tidal radius it has a size of roughly 1 AU. That's the distance between Earth and the sun. The thermal radius is 30 AU. This is the distance where you actually see most of the photons coming from. And finally, the scattering radius, that's the radius, that's the distance that you actually see in terms of polarization. So that's the final distance where you get electron scattering. So beyond this R scattering, there are not enough electrons to scatter the photons. But below this radius, there are too many electrons that you get lots of scatterings. So there's that sweet spot at about 100 AU. In comparison, the solar system is the size of roughly 30 AU. So this gas cloud around the black hole and around the accretion disk is much, much bigger than the solar system. It's very big. Right, so that was at maximum light. So at maximum light, we see zero polarization. But a month later, what we see is that the polarization actually kind of increases. So same stuff here, and just if you focus on the middle panel here, the polarization actually goes from 0% up to roughly 1%. And what we think is happening is that as time goes on, the scattering radius, the thermal radius sort of shrink inwards. And as they shrink inwards, you are seeing more and more of the accretion disk. And it's possible that the accretion disk is asymmetric inside. So that's where the current results are, and that's what they tell us. So initially, at maximum light, you see a very spherical cloud, which is consistent with the reprocessing model. And at later times, as the outflow weakens, you can actually see slightly more interior regions. And the hope was, if we could get more data up to later times, we would actually see even more polarization. So going back to that question that I asked towards the beginning. So now what we see is that, the data are telling us that there is a strong outflow of wind. So what turns out is that actually only a very small fraction of that initial star's gas falls onto the black hole. Roughly half of it goes in unbound orbits, and for whatever is left that will eventually form the accretion disk, only a small fraction of that will actually eventually accrete onto the black hole. Much of that mass is lost in wind outflows. So that is, a very different picture from the picture that I initially thought growing up, that, black holes are just out there to get you. It's actually, it's weird to think that much of that mass doesn't actually fall onto the black hole, it just, flies away. So here are some takeaway points. So TDEs, they help us study black holes in very distant galaxies. Not everyone has a gravitational wave detector in their backyard. So it's we can't study black holes that way. It's a lot easier to study TDEs. The rate of TDEs is roughly like, in a given galaxy, they happen once every 10,000 years or so. But the fact that there are so many galaxies out there means that you do observe roughly a dozen of them every year. So the other point is that the classical TDEs were expected to show X-ray emission, but many TDEs were found to show more visible light. And it's currently unclear why that was the case. And there are two models, the reprocessing model and the shocks model, that attempt to explain why TDEs have so much optical emission. And the polarized light from one TDE supports the reprocessing model. Now, since that paper came out earlier this year, there have been some other papers that sort of provide an alternative picture about what's happening in the gas. Some of those measurements are very high polarization, like 25% polarization. But remember, I said that the most polarization you can get is roughly around 11%. So that's sort of inconsistent with the physical picture. It's not at all clear how you could get such very high polarization without some non-thermal processes going on. So so this is a very new field right now. TDEs only, even though the theoretical framework for TDEs was set in the 70s and the 80s, the observations are only just now catching up. And I think the crucial bit is to understand what's happening to the gas around the black hole, and the studying polarized light is a great way of doing that. Yeah, so I think I'll stop here. There are roughly 10 minutes left, and I'd be happy to take any questions, or in general, happy to talk about, how I landed on this project, starting from exoplanets as an undergrad. So yeah.
Any questions for our speaker?
Yeah.
So, polarized light, do you use spectroscopic polarimetry? Is that the main way of studying polarized light?
Yeah. So the technique.
Can you repeat the question?
Okay. So the question is that, what's the technique that we use to study polarized light? What it is? Can you describe it a bit more? So the technique that we use is called spectropolarimetry. So polarimetry means the study of polarized light, and spectral as a prefix means you divide that as a function of wavelength. So spectropolarimetry means you study the level of polarization as a function of wavelength. There is another technique called imaging polarimetry, in which you just take images of the of some astronomical object in different polarizing filters and try to estimate how much of the light is polarized in that way. But spectropolarimetry, studying the spectrum of the polarization, is way more useful because it can tell you some wavelength dependence that is actually, important in understanding, for example, how the dust behaves in that gas, or for example, if you have any emission lines or absorption lines, what kind of geometry do those lines have? So spectropolarimetry is a lot more richer in terms of the information buried in there. That also means the flip side of the coin there is that spectropolarimetry is a lot harder to understand than imaging polarimetry. The interpretation is a lot unclear. Yeah. More questions?
Yeah, I guess I had a question about
Yeah.
the very basic, but you mentioned the star orbiting the black hole, and some of it gets blown out and some of it forms an accretion disk, you said?
Yeah.
Does the accretion disk just kind of last forever, or does that eventually get sucked in?
Yeah. So the accretion disk, it has some size to it. And the innermost region of the accretion disk is actually feeding material onto the black hole. So over time, you would find that the accretion disk gets smaller and smaller, and then it disappears. The time scale over which that happens is still unclear. But in the case of TDEs, the fact that the brightness, rises in 60 days and then goes off and becomes undetectable in roughly a year. So we expect that the lifetime of an accretion disk might be on the order of 1 year or a few years. Yeah. But I think one important distinction that I think I should make is that, the images that you saw at the beginning of the black hole from the Event Horizon Telescope, those disks are not from a tidal disruption event. They are something called an AGN, the active galactic nucleus. And what's that is that you just have lots of gas near the black hole that has formed this giant disk over, millions or billions of years. And those disks are, compared to the tidal disruption event, more permanent. There's simply just too much mass in those disks. Whereas a tidal disruption event is just one star. Yeah. Yeah.
You mentioned that other papers suggest that a high percentage polarization might correspond to, or there might be evidence of some non-thermal processes. What kind of non-thermal processes are in TDEs, and do models accurately match the brightness energetics that you see? Basically, does the theory match operations? In supernovae, we have issues where our models cannot reproduce the high energies that we observe there.
Yeah. So imagine you have an accretion disk that's spinning around, and you have charged particles in that accretion disk. So you have a current going around the black hole. That current forms very strong magnetic fields. And those magnetic fields can occasionally launch jets in the polar directions of the accretion disk. Now, it's not exactly clear how those jets are formed in the first place. That's still very much an open question. But once you have those jets, you have these particles that are accelerated at very high velocities. And some of them are spiraling upwards, spiraling out. And each time you accelerate a charge, you create radiation. And in this case, when you accelerate charge at relativistic speeds, the kind of radiation that you get is known as synchrotron emission. And synchrotron emission can be polarized up to 60, 70%. So it's very high level of polarization. So that's what I mean by non-thermal process. It's because of the magnetic fields that you are getting polarization and not because of any geometrical effects. In TDEs, if you have a jet, then it's possible that you have enough energy to get polarization in the synchrotron range. But if you don't have a jet, then I think there's no reason to believe that the magnetic fields are strong enough to contaminate your polarization measurement.
Any other questions for us? Let's take our speaker one more time.
Thank you for having me.